Good evening, Professor Ben Liang and Professor Gangwar. Welcome this third day of ongoing Spark course on dielectric resonator and its application. Like 2-3 minutes, we will take more to start the session.
It's good to see you, Professor Leong.
Yeah, nice to meet you.
Yeah, I have visited your place in 2015.
Oh, really?
Yeah, there is one conference on computational electromagnetics.
Oh, I see.
Yeah.
I see. Yeah.
So that time I have visited your laboratory also during these 3 days.
So when will you come again?
Yeah, that was the great experience with me. Very nicely managed, and everything is very in the very proper timing, and each and everything, the special lectures are extraordinaries, and the gathering of all over world, the professors are marvelous at that time. Professor that P.K. Sarkar is there, and Raj Mitra is there, and many more. There are very stalwarts are there. So the first time for me to visit that place and to meet each and everyone personally at that time. Also, Professor Kisk is there at that time also.
Yeah. Do you like Hong Kong?
Yeah, definitely. It's very cool and very nice place.
Then you should come again.
Yeah, definitely. If you organize any one conference next year, then I will definitely try to come.
We have APMC 2020.
Yeah. I have seen APMC. Yes.
But it will be an online conference.
Yeah, definitely. Then I will try to come and meet you again.
Yeah. Okay. Good.
Well, good evening, good afternoon, and good morning. I, Dr. Taimur Khan, convener of this webinar, welcome you all again to the third day of 1 week-long ongoing Indo-Canada Spark course on dielectric resonator and its applications, DRA-2020, organized by National Institute of Technology, Silchar, India, Delhi Technological University, Delhi, India, and Queen's University, Kingston, Canada, and hosted by Electronics and Communication Engineering Department, NIT Silchar. I am extremely delighted to have 3 distinguished speakers, Professor Wok Leong from City University of Hong Kong, Professor R.K. Gangwar from Indian Institute of Technology, Indian School of Mines, Dhanbad, India, and Professor Bhaskar Gupta from Jadapur University, Calcutta, India, for today's 3 consecutive sessions. In the continuation of day 1, may I directly request to Professor Ben Liang to start the session.
Okay, yes. So I share my screen first.
Yes, yes, now you can share.
Okay, to begin, I would like to thank Dr. Khan for the kind invitation so that I have this opportunity to share the research work of my team to everybody. Okay, today I'm going to share with all of you the recent development of DRA at my research group. Now, this is an introduction slide, and I believe all of you know the properties and the advantages of DRA very well. Okay, the first technical slide is to share with you wideband omnidirectional DRA. Okay, here, okay, let me take a laser pointer. Okay, this is a 2-layer transparent DRA. Now the outer layer is glass, whereas the inner layer is acrylic plastic, which is transparent. Now, for this transparent DRA, we insert 2 LEDs so that it can be used as a light source. For this wideband design, the basic theory is that we have a glass layer between air and the inner acrylic plastic. Because of this layer, the impedance can be matched very well, and we can obtain a wideband design. So this is a wideband design. The bandwidth can be increased from 14% to 32% by using the 2-layer structure. Now, these are the radiation patterns at different frequencies across the passband, the -10 dB impedance level. And we can see that the radiation pattern is very stable across the passband. Okay, next, I'm going to discuss dual-mode rectangular DRAs. Now, this is a basic rectangular DRA resting on a ground plane. Now, the first 3 resonant modes of this rectangular DRA is TE111, TE112, and TE113 without the ground plane. That means the ground plane actually is located at the middle of these 3 DRAs. The lower one is in fact the image of the ground plane. However, if there's really the ground plane existing in the structure, the E field here, this is E field, which is strong at the ground plane position, which violates the boundary condition that the tangential electric field should be 0 on the ground plane or on a metal plate. Therefore, this TE112 mode cannot be excited when we consider the use of the ground plane. And as a result, for the dual mode design, we make use of TE111 and TE113. Now, these are animations for the TE111 mode field and also TE113 mode field. Now, we can see that for the fundamental mode, we have only one half pattern, but for the higher order 113 mode, we have one full here and one half here. So it is, if we look at the center, we have one full loop and half loop as shown in this animation, one full and one half. Now to analyze the rectangular DRA, we can use the dielectric waveguide model. Now for TE111 mode, the resonant frequency can be calculated by using this formula with KY1 solved by this transcendental equation. Now, if it is the fundamental TE111 mode, KZ is equal to pi over 2D. So we have a coefficient of 1 before pi. But for TE113 mode, the coefficient before pi for the Z direction wave number is 3. It is because if we consider the image structure, so the image below the ground plane is considered, then we have, for the fundamental mode, we have only one loop. You can see one loop. But for TE113 mode, we have 3 loops, 1, 2, and 3. Therefore, here, along the Z direction, we have 1 and 3. For KZ1, excuse me, KX1, it is the same for the fundamental mode and the high order TE113 mode. In other words, KX1 and KX2 are equal. And of course, for a different mode, KY2 needs to be calculated by using the same dielectric waveguide model formula. Okay, we generated a large number of data sets by using this dielectric waveguide model. And then we use the curve fitting technique to obtain engineering formulas to calculate the dimensions of the dual mode DRA. Now, without this formula, one would need to use the trial and error method to obtain 2 different frequency modes for a rectangular DRA. This can be very time consuming. But with these formulas for the dimension A, D, B. Okay, A is here, A, B, D. For a given dielectric constant, then we don't need to go through the painful trial and error process. Okay, after using the curve fitting technique, we obtain A given by this formula, D given by this formula, and B given by this formula. Now, B1, B2 are given by this formula, and delta D is given by this formula. Now, K1 and K2 are the wave number at frequency F1 and F2. F1 is the frequency of the TE111 mode, whereas K2 is the frequency of the TE113 mode. Now, there's a new knowledge from our engineering formulas. Now, from the previous slide, we have A given by this. And from this, we have inside the square root must be a positive value. Therefore, this is larger than or equal to 0. And from this, we have 3 K1 larger than K2. And we have this, and then we have this conclusion: F2 over F1, F2 over F1 is less than 3. Now, this information was not found before our formulas. Therefore, without this knowledge, one may try to design two different frequencies with the ratio larger than 3. In that case, he or she would spend very long time, but will fail to obtain a solution because it exists a limit. So this is very important to know this limit so that we will not waste our time to do something which is meaningless. If we try to use a rectangular DRA to obtain two frequencies using TE111 and TE113 with frequency ratio higher than 3, it is meaningless and just waste his or her time. Okay, we have done an error analysis for our formulas. We compare our results with the DWM, dielectric waveguide model result. And we found that the error is less than 2.5% for the frequency ratio between 1 and 2.8. And for epsilon R, which is the dielectric constant between 5 and 70. Okay, this is an example for using our formula. Suppose we want to design a dual band rectangular DRA with frequency F1 equal to around 3.5 gigahertz for the Ymax frequency, and the second frequency is 5.2 gigahertz for wireless LAN frequency, and we are given a material of dielectric constant equal to 10. By using our dual mode formulas, now A is given by this, B, and D. Now, as you can see from this slide that it's not very easy and convenient to design a dual band rectangular DRA without going through the painful trial and error process. We use a slot coupled DRA for this dual band design. These are the dimensions of the fitting structure and the substrate. Now, it should be mentioned that our engineering formulas can provide the dimensions of the rectangular DRA only. However, it cannot provide any return loss or antenna gain information. Therefore, we will use HFSS to simulate the reflection coefficient, antenna gain, and radiation pattern. Now, these are the measured and simulated reflection coefficients. A pretty good agreement between simulation and measurement is found. Now, at the lower band, the bandwidth is 15%. This is for minus 10 dB impedance level. This is the frequency range. That means here. It covers the Ymax frequency very well. And the upper band, 10 dB is around here. The measured bandwidth is 8.3% for this frequency range. And it covers the 5.2 wireless LAN band very well. Now, this is a comparison table for our design, simulated, and measured resonant frequencies. Now, this is the fundamental mode. Our design frequencies are given here, 3.47, 2.0, and 5.30. And this error is compared with this measurement. So the error between our design frequency and the measurement is 3.47. Excuse me, it's 2.05%. And for the higher order mode, our design frequency is here, and the measured frequency is here, and the error is 2.32%. And after doing the simulation by HFSS, we have found the resonant frequency 3.47 and 5.24. Now, the error between the simulation and the measurement is 2.05 and 1.15. So all the errors are less than 2.5%. So it is very acceptable. This is the measured and simulated radiation pattern for the TE111 mode, the lower band radiation pattern. Now, we obtained the broadside radiation patterns as expected for TE111. And we have the co-polarized field larger than cross-polarized field by more than 20% in the broadside direction. So this direction. Okay, next, we see our measured and simulated radiation pattern for the high order mode. Again, the broadside radiation patterns are obtained because TE111 and TE113 are from the same mode family. Therefore, their radiation patterns are similar, except that the higher the order of the mode, the narrower the beam width of the radiation pattern. That means if a high order mode is used, then the antenna gain is higher and the beam width is narrower. For this higher order mode, the co-polarized field is larger than the cross-polarized field by 20% in the broadside direction. It's the same as for the fundamental TE111 mode. This is the measured antenna gain. Now, for the fundamental mode, the gain is about 4.02 dBi. And for the high order mode, it is 7.2 dBi. Now, at the high order mode, the gain is higher than that in the lower frequency mode. It is because it is known that an electrically larger antenna has a higher antenna gain. Now, because we have a single DRA at the higher frequency, it would become electrically larger, and therefore it is reasonable that its gain is higher. Okay, next we consider an example for a wideband DRA design using the engineering formulas. Now here, to have the wideband design, the idea is to merge two resonant modes together. So here we have two resonant frequencies which are not too far away from each other, 1.98 and 2.48. By using the engineering formulas, we have the dimensions of the rectangular DRA given by 30.7 millimeter, 24.7 millimeter, 47.7 millimeter, with dielectric constant equal to 10. Now, this dielectric constant is an input parameter for our engineering formulas. Okay, in this case, we use a conformal strip here stuck on the surface of the DRA to excite the antenna. Now, the strip has a length of 17 millimeter with a width of 1 millimeter. This is a aluminum ground plane. Okay, now this is the first mode. This is the second mode. And because they are not too far away from each other, the two modes merge together, and therefore you obtain a wide impedance bandwidth. Now the bandwidth is about 31%, from 1.83 gigahertz to 2.50 gigahertz. Now this band well covers PCS band, UMTS, and wireless LAN band. Again, we check the radiation patterns. Very conventional broadside radiation pattern is obtained as expected. Now, the co-pole is larger than the cross-pole by 20 dB in broadside direction again. So here, we consider another frequency, around 2.4 gigahertz. We can see that agreement between simulation and measurement is also very reasonable. And with the polarization purity higher than 20 dB. Now this is the measured antenna gain. Again, when the frequency is higher, the gain is larger, which is expected. Now, this is the fundamental mode. This is the high order mode. Okay, next, we consider the dual mode cylindrical DRA design. Now, this is cylindrical DRA resting on a ground plane. Now, the formula or the equation relating the different wave numbers is given by this formula. We have K rho I and KZI are the dielectric wave numbers along the rho and Z directions respectively. And K log I is the wave number in air. So Fi is the frequency that we want the DRA to have. And therefore, if we know the formula for K rho and Kc, then we can determine the dimension A, radius, and the height h of the cylindrical DRA. So we need to analyze K rho and Kc. Now this is the equation for K rho. In the analysis, we assume an infinite dielectric rod. Now K rho I prime, here we have some without prime and some with prime. The one with prime is given by this formula. Jm is the Bessel function of the first kind, and Km is the modified Bessel function of the second kind. Okay, after knowing K rho, then we need to determine Kz. For Kz, we considered an infinite dimension in the lateral direction. So from this infinite dielectric slab, we have this formula relating the different parameters. Now, the thickness of this dielectric slab is h, which is the height of our DR. Again, based on these two parameters, K rho and Kz, we generate a huge number of data sets. And then we use the curve fitting technique to determine the dimensions of the cylindrical DRA. Okay, F1 is the frequency of the lower band, and F2 is the frequency of the upper band. We use the covariance matrix adaptation evolution strategy to do the optimization and obtain our ratio h over a. Now, the parameters are given by this matrix. This matrix was obtained by using this evolutionary strategy. Now, by using the analysis, we have A given by this. And now the different parameters are given by this matrix. Again, this matrix was obtained by using this covariance matrix adaptation evolutionary strategy. Now, after H is found, then H can be obtained by this formula. Okay, we have checked the error. The error is given by 2.1% for this frequency range, for this dimension ratio, and for this dielectric constant. And the maximum error of H is given by 3% for this dimension ratio and dielectric constant. Okay, here we have an example. For the dual band design, we design 1.7 and 2.4 by using the formulas 1 and 2. This is 1, 2. and we have A given by this and H given by this. Okay, we use the conformal strip to excite this cylindrical DRA. Here we introduce a slot to facilitate the matching. Now this is the coaxial aperture here, coaxial aperture. Okay, these are the parameters of the antenna. In our simulation, we have slightly increased A from 17.9 millimeter to 18.7 millimeter here to optimize the result. Now this is the mansard and simulated reflection coefficients. We can see that pretty good agreement is obtained. Now the lower band impedance bandwidth is 15.5%, whereas the upper band bandwidth is 3.7%. Now this is the simulate and mansard radiation pattern for the lower band and upper band. Again, the agreement is very reasonable. The co-polarized fields is higher than the cross-polarized field by 20%, 20 dB in both sides direction. This is the mansard and simulated gain. Now for the lower band, the gain is about 6 dBi, and for the upper band gain, its value is about 8 dBi. Now the higher value for the higher order mode is expected because, as said before, at the high frequency, the DRA is electrically larger, and therefore its gain is larger, which is reasonable. Okay, next we consider the circularly polarized DRA for the dual band design. Here, now if we consider one conformal strip fit and one matching knot, one matching slot, we have LP design. To obtain a CP design, we have another fitting for the DRA with 90 degrees phase change and 90 degrees displacement angularly. And here we have a dual band hybrid coupler. Now with this dual fit, we can obtain a CP design. These are the parameters of the design. We have the lower band and upper band for simulation and measurement. Now, for the lower band bandwidth, it is about 90%. Upper bandwidth is 7.8%. This is the SO ratio. This is the lower band SO ratio. Its bandwidth is 12.4%, whereas the upper band SO ratio bandwidth is 7.4%. These are the simulate and mansard radiation patterns. Their respective frequencies for the two modes. This shows the purity, polarization purity of the CP design is higher than 20 dB in the both sides direction. Okay, next we consider the wideband design. Now we consider 2.9 and 3.72 by using the formula. We have this. Now we use the conformal strip. Here, as we can see, the two modes merge together, and therefore we obtain a wide bandwidth. It is 23.5%. This is the mansard and simulated gain. At the lower band, the gain is lower. It's 7 dBi. At the upper band, the gain is 10 dBi. Just now we have seen a wideband linear polarized design, and now we consider a wideband CP design. We use the same idea. We have a second fit, which is 90 degrees phase difference, and also the two fields are displaced angularly by 90 degrees. These are the parameters of the design. Now, we obtained a wideband in reflection coefficient and also a wide axial ratio. Now, the wide axial ratio is 24.7%. Here, we have used a wideband hybrid coupler. Next, I will show you a circularly polarized design. Okay, here, it is a conventional DRA, which is made of glass, so that we can use LED to use this DRA as a light source. Now, the CP is obtained by modifying the ground plane. Here, we introduce a spiral-shaped ground. So here you can see very clearly. We remove some metal on the ground and obtain a spiral-like ground plane. And because of this spiral-like ground plane structure, a CP can be generated. Now, the good of this design is that we can obtain a CP antenna by using a simple DRA. We don't need to introduce any patch or change its structure, or truncate its corner, etc., to obtain a CP antenna. It's just a simple conventional DR. Okay, to save time, I would like to skip the result. Okay, next. I'm going to share with you the pattern diversity DRA designs at my research team. Okay, the first pattern diversity design is to use two fundamental modes. Okay, why do we want to use fundamental modes? It's because if we use a higher order mode, then as I said before, for higher order modes, then the beam width will be narrower, and therefore it may not fit certain applications. Of course, it depends on the objective of your applications. But some applications would like to have a wider beam width so that it can have a larger coverage. So these are the comparison between the high order mode and fundamental mode. Now, for impedance bandwidth, the fundamental mode has a wider bandwidth. It's because for high order mode, the Q factor is higher, and therefore the beam width is wider. And for beam width, as I said several times, high order modes has a narrower beam width. Okay, now we use two fundamental modes. One fundamental mode is for the TM mode. The second fundamental mode is for HEM family, HEM mode family. Now, as we can see from this graph, the two modes do not have any intersection. But for the diversity design, we need to have the same operating frequency. So we cannot use these two fundamental modes directly. Okay, I modified my saying. We use these two modes, but we cannot use a simple DRA directly. Okay, and then how to make the resonant frequencies of these two fundamental modes the same? This is the challenge of this project. Now, to solve the problem, that means to obtain the same frequency for the two fundamental modes, we analyze the field inside the DRA. Now, for the HEM moment delta mode, which is represented by the red dot line, the field is like this. as we can see clearly here. For the TM mode, the fundamental TM01 delta mode, which is represented by the blue line, is field is like this. Now we can see clearly that at the central region, it is mainly the TM mode field. For HEM mode field, the central region is much less. And it suggests an idea that we can put a higher dielectric material inside this region so that it will affect the TM mode significantly, but will not affect the HEM moment delta mode significantly. Now, also observe that, go back to this graph. The TM mode has a higher frequency. Therefore, we introduce a higher dielectric constant material so that it will shift the frequency of the TM mode to a lower value. When it has a lower value, hopefully it will have some intersection with this HEM moment delta mode, because for diversity design, we need to have the same frequency for the two modes. And therefore, we introduce a zirconia cylinder inside the central region. Now, by introducing this zirconia dielectric region inside the center part, we have the frequency given by this TM mode. Now we have an intersection point with the HEM moment delta mode. Okay, we can look at this. Now R1 is the radius of the internally loaded DR, which is zirconia. Now, if we change the radius of this zirconia, we can see that the frequency will shift to the lower side. That means the larger the zirconia, then the smaller the frequency, which is expected. But for the for the fundamental HEM moment delta mode, the frequency does not change significantly when the size of the zirconia is changed. So 2, 4, 6, 8, 10 is the same as here, 2, 4, 6, 8, 10. For the lower, for the TM mode, it changed significantly. For the HEM mode, it has no change, which can be expected from this field distribution. So our operating frequency will be obtained at this dimension, R1, which is the radius of the zirconia. Okay, this is the configuration. Here, we have the glass DRA. We have a hollow region to insert the zirconia. And we have the probe fit. This is the probe which fit the DRA at the center position. So here, this is the center position. We have a probe. And we have a slot fed HEM moment delta mode. We use a fork shape fit 9 to fit the slot at this point and this point. Here, we use a cross slot instead of a simple straight slot, because we want to have more rotational directory, rotational symmetric structure, which is important for the TM mode. So this is the side view. This is zirconia. This is the probe. Now this is the mansert and simulate result. We have the TM mode result and HEM mode result. And the isolation between them is very good. For the band we are concerned with, about the 2.4 wireless LAN band, it is lower than 34 dB. Now, this high isolation can be expected because if we go back to here, basically the fields of the HEM mode and TM mode are orthogonal. Because they are orthogonal, their interference is not significant, explaining why we have such a good isolation. Now, although our application is for the 2.4 wireless LAN band, actually, the overlapping bandwidth between TM mode and HEM mode is 23.4%. Now, this very wide usable bandwidth for this diversity antenna is the widest one among the reported pattern diversity DRAs. Now, this wide bandwidth is because we use the fundamental modes for TM and HEM mode families. Okay, these are the realized gain and for the HEM mode and for TM mode. For TM mode, the gain is about 1.6 dBi at theta equal to 45 degrees. So here, the maximum gain is around this angle. For HEM port, it is broadside mode, so we measured the broadside gain. It is 5.4 dBi. Now the efficiency is 85% across this 2.4 wireless LAN band. This is the efficiency. So across this wireless LAN band, it is about 85%. So that's the latest patterns. Very good agreement between simulation and measurement is obtained. Now, the cross-pole level is less than minus 20 dB for HEM port. For TM port, it is less than 20 dB. So the polarization purity is pretty good. For diversity antenna design, we need to know the ECC, which is envelope correlation coefficient. And we have done measurement. We found that it is much less than 0.5, which is the criteria for practical diversity antenna in the industry. Okay, in our simulation and measurement, we use this very fundamental ECC formula. Some people use the S parameters to calculate the ECC, but this one is most accurate because it is in fact the definition of ECC. Okay, next, I'm going to introduce a second diversity design. Okay, here we consider single feed first, and then we will introduce a second feed for the diversity design. So here it is only a single feed LP design. Okay, to excite the DRA, we use an annular slot, but now it is not a conventional annular slot, but instead some inductive elements are introduced inside the slot. Now, by introducing these inductive elements around the slot, then we have the resonant frequency of the DRA becomes much lower. So this is the fabricated antenna. This is the slot loaded by this inductive structure. Okay, now without the annular slot, without the inductive structure, a simple annular slot will excite HEM moment delta mode, which is broadside mode. Now, if we plot the electric field along the annular slot, we will find that the field, E field, is not uniform across the slot, which is well known for the HEM1 delta mode. And for this new annular slot with inductive elements introduced, we can see that the E field is now much more uniform as compared with this one. Now, what is the good of having a uniform E field around the slot? It can be modeled as a magnetic ring, a uniform magnetic ring current. If we have a uniform magnetic ring current, then we can excite the TM mode of the DRA. Now, this is the good of the design, because now, if we go back here, this is the bottom of the DRA. You don't see any hole for probe penetration, because for many years, we use probe to feed axially at the center position to excite the TM mode. But now, with this uniform magnetic current distribution around the slot, we don't need to use the probe feed method. In fact, as we can see here, the DRA is very simple. You don't need to do any hole drilling or trying to use any method to modify the DRA. No, you don't need to do that. So this is the advantage of our design. Okay, now we consider our diversity design. Now this is the TM port. To have the diversity, we use another mode, HEM moment delta mode, to obtain a pattern diversity design. Now we use a differential fit to obtain a good radiation pattern. So this is the strip fit, and the other side we have another strip for the differential fit. So these two solder point is for this and the other side. For this part, it is the original TMO design. So these are the TMO result and HEM moment delta mode result. And this is the isolation. As can be expected, the isolation is very good. It's below 30 dB. It's because the TM01 delta mode field is orthogonal to the HEM moment delta mode field. Now the overlap bandwidth is 5.7%. These are the realized gain and antenna efficiency for the two modes. Okay, I would like to go to the next slide. These are the radius pattern, the broadside mode, and the omnidirectional mode for TM port. This is the ECC. It is less than 0.001. So it satisfies this criteria very, very much. Okay, next we consider polarization diversity. Now the first polarization diversity DRA was done about 20 years back by the research group in Taiwan. They used one port here and the second port here to excite the rectangular DRA. And because they excite the two orthogonal modes or degenerate modes, the two degenerate modes do not interfere with each other. Therefore, their isolation is very good, 20 dB. These are the results. S11 and S21 is isolation. Okay, there's another research group in Australia by Dr. Thermal's group. Okay, here they used TE01 delta mode and TM01 delta mode. For TM mode, they use T-shaped probe here, T-shaped probe. And for the TE mode, they use this alpha loop, the alpha loop to excite the TE mode. So these are their results. S11 for port 1 here, and S22 for port 2 here. Now, port 2 is the TM mode. Port 1 is the TE mode. This is the isolation. As we can see, the isolation is about 18 dB for the frequency band that they are concerned with. Okay, this is polarization diversity design at my research group. Okay, we use the formula that I have presented in the early part of my presentation. By using that formula for dual band design, we obtain the radius and the height. Here, we introduce the matching slot, and we have the overlapping bandwidth, 16.2% and 7% for lower band and upper band respectively. This is the gain and antenna efficiency. So this is the gain. These are the antenna efficiency. Radiation patterns. Port 1 and port 2, lower band and upper band. Okay, we have dual band and we can also have wide band. Now, again, we apply our previous knowledge of the engineering formulas for wideband DRA design, and then we can obtain this polarization diversity antenna with a wideband characteristic. Okay, we use HEM111 mode and HEM11 free mode for 11 delta and 11 delta plus 2. So isolation very good. Okay, I want to go to the slide. Okay, next, we consider another design for the polarization diversity DRA. Here we use a planar fit for the TM mode. Now with this planar fit, we don't need the probe fit penetration. Now this is the microstrip cross with shorting pins at the 4 ends of the cross. Now, as we can see, it is a TM mode. Okay, for diversity design, we want to have a second mode, which is TE mode family. Now, originally, we want to have TE01 delta mode. However, as there are two problems. The first problem is that we cannot have an intersection with the TM mode. That means we cannot have the same frequency for TM mode and TE mode. This is the first problem. But larger problem is that actually TE01 delta mode does not exist when the ground plane is here, supporting the DRA. Now, this is the mode of an isolated DRA. As we can see, the E field, excuse me, this H field. The H field is very strong here, very strong. So this cannot be supported when the ground plane is here. However, if we consider TE01 plus delta mode, the H field is tangential on the ground plane. In this case, this mode can be supported. So here, if we go back for Dr. Foymo's design, they use TE01 delta mode. So in fact, this mode in general should not be supported by a grounded DRA. Can be analyzed here. So we use O11 plus delta mode for the TE mode. Okay, now the this part, the cross patch, is to excite the TM mode. Here we have the alpha lobe to excite the TE mode. So we have the diversity antenna. Okay, this is the fabricated antenna. One port is for TE, the other port is for TM. Now this is the S parameters, a TM port and TE port. Okay, here I should mention that for the pattern diversity design, I also use TM and TE modes. But in that case, the TE mode is for the broadside mode. But here, the TE mode is also omnidirectional. In other words, both TE and TM modes are omnidirectional for this design. And therefore, the radiation pattern are basically the same or very similar. So the diversity here is not from the pattern, but from the polarization. Okay, the overlapping bandwidth is 8.1%. This is the TM port. This is the TE port. This table summarizes the results. This is the antenna efficiency. For the TE011 plus delta mode, we have impedance bandwidth given by this antenna gain and total efficiency. The total efficiency has taken into account the impedance matching. So it's TM mode. The gain is 2 dBi, which is better than the TE mode. For TE mode, in fact, the structure is more complicated, as you can see from the alpha lobe. And therefore, it is not surprising that its loss will be higher, and therefore the gain is lower. And it can be reflected from this efficiency, it is lower because of the more complicated structure. Well, this is the TE port radius pattern and TM port radius pattern. Now, as we can see, both of them give us omnidirectional pattern. This is the elevation plane. This one and this one is the elevation plane. And this one is the horizontal plane. Okay, here we can see the E field. For TE port, it is like this. For TM port, it is in the elevation plane. And for H field, it's the reverse. For TE port, it is like this one, magnetic dipole. For TM port, it is like electric dipole. Okay, next we are going to apply our polarization diversity design for our Wi-Fi router here. Okay, this is our box. Inside the box is a router PCB. So we take the PCB out from a commercial router. So this is the design that I have already presented. Okay, in our comparison with a commercial product, we choose this 360 P1 router, which was bought from the commercial market. Okay, we use its PCB. Okay, we take it. In fact, we bought several 360 P1 routers, and one of the routers has been removed is PCB to transfer to this our Wi-Fi router design. And we have a phone for sending Wi-Fi signal. And we use an apps, these apps, to measure the reception of the Wi-Fi signal. Now, this is the screenshot of this app on the mobile phone. Okay, this is the floor plan of our stage key lab. Now, here is our router here, our router, and also the commercial router. So at one time we test one router, and then we test the second router, and then we take this testing mobile phone and move it around different locations of our stage lab. And then from these apps, we find out the reading, the Wi-Fi reception reading, and then we record the reading. Now, the orange bar is for our router design. The gray bar is for the commercial product. Now, because we use the same PCB of this commercial product, so the comparison is very fair. Okay, what's the result? Okay, we can see that for the commercial design, they use two monopole antennas. When it is near the antenna, either our router or the commercial router, the reading given here, they are similar, and the commercial router has a better result. But it doesn't matter because the signal is very strong. So a slightly stronger signal makes no big difference. What makes a big difference is that when the signal is poor, whether your router works or does not work. Okay, let's see when the testing point is far away from our router, say outside our stage lab. You see, when outside the stage lab, the signal will become much weaker. Now, our router gives a better performance. And also, when it's far away from this point, because here we have many benches, some tables, and some other stuff, which are not shown here. So the signal from here to here will not be a very simple path. And therefore, it can test the ability of the antenna design very clearly. Here you can see that the commercial router gave a very poor reception. But for our router, you see the reception is still very good. And here, which is at another location, which is far away from this our router. Now the mobile phone here can receive a better signal than when using the commercial router. So this demonstrates that the performance of our diversity design is better than the simple two monopole design. Here, let's see a video. Okay. It needs to change back to the pointer. Yeah. Let me see how to. Oh, okay. Yeah. Okay. Okay. Before we proceed, let me briefly tell you the story. Now, this girl is using a mobile phone, and he used the data to communicate with her boyfriend. And unfortunately, she used up the data of her mobile phone plan. And therefore, in this mass transit railway, she failed to communicate with her boyfriend. And then she returned home and used Wi-Fi to communicate with her boyfriend. And then let's see what happened. Okay, now here, the data is used up. She has no more data to communicate with her boyfriend. So she is frustrated. Now she returns home. And now she can use Wi-Fi to communicate with her boyfriend. Unfortunately, the Wi-Fi signal is not good. Now with the glass antenna on, the Wi-Fi signal is very good. Okay, apart from the two-port design, we have also done a three-port polarization and pattern diversity design. Now the polarization diversity comes from this one and this one. They make use of two degenerate DRA modes, and pattern design because the third port use a probe. So the first and second ports have polarization diversity with broadside radius pattern. The third one introduced the pattern diversity to the first two because it has a different radiation pattern. So we can see here, this is port 1, port 2. Okay, port 1 is here. Okay, port 1 is here. Port 2 and port 3. Port 2 and port 3 are both broadside radiation modes. But they are, the phase are displaced by 90 degrees. So finally, I would like to share with you mirror DRA. Okay, here we have glass on top of this DRA. Now, this glass is in fact a second dielectric layer for this DRA. So it is not simply just stick a conventional mirror onto it, but instead it is part of the DRA design. Okay, this is the summary of my presentation. We have presented some dual and wideband DRA by using two dielectric layers, high order modes, and special fitting structure. We have presented pattern and polarization diversity DRA, and also we have applied one of the polarization diversity DRA to our router design. Thank you very much.
Thank you, Professor Liang, for a wonderful and informative session. Now, 2-3 queries are there on your presentation from participant side. First one is, suppose a meta surface is stacked between two cylindrical DRAs. How the boundary condition will be used for that stacked form?
Which cylindrical DRA you are referring to?
Okay.
Is it this one? Okay, but please let me know if I move to the right slide.
I think this query is not in context of any your PPT. It is, I think, journal query from the participant. If a meta surface is stacked between two cylindrical DRA, then what will be the boundary conditions criteria for that?
You mean use the DRA
Yeah.
to form a meta surface?
Yeah. Meta surface.
Now, if you use the DRA to form a meta surface, then I want to know whether the objective is a DRA array or it is not for antenna purpose.
Okay. Let us anyway, sir. No problem. Let us move to another query because it is already 10 minutes late. Please suggest some references either in published paper or textbook where designed equations can be found for different shapes of DRA. Would you suggest some references?
References for which design?
All fundamental DRAs, fundamental shape of DRA design equations.
Oh yeah, Pitosa from Canada has a very good reference textbook.
Okay.
Research book, I would say research book. It is published by Arctic House.
Yeah. Okay. The last and third query is in ultra-wideband DRA, how to calculate the frequencies?
For wideband DRA.
Ultra-wideband.
Ultra-wideband.
Yeah.
Now for ultra-wideband, then you need to combine many different modes of the DRA. And also you will need to include the monopole mode. So it is not a single formula that can give the frequency because it will involve many different modes.
Yeah. Okay. With this, thank you very much, Professor Ben Leong, for accepting our invitation and for agreeing to deliver these two expert lectures in spite of different time zones from your region. Then special thanks for informative deliveries in both the lectures. 3D glass antennas followed with some recent development. Thank you once again, Professor Leong, for being with us in these two different sessions. Thank you once again, and see you in some other occasions. Bye. Have a night. Good night.
Okay. Good night. Thank you.
Bye.
Bye.
Good night, Professor Leong.
Yeah.
Now, as a second speaker of this third day session, Professor R.K. Gangwar from IIT Dhanbad is with us. He has already joined us prior to this lecture. In continuation of day 2 session, I welcome and I directly invite Professor Gangwar to start the session.
Okay, thank you very much, Professor Khan. So, is my PPT is visible?
Yeah.
Yeah, thank you. So today I am going to be discuss about the understanding of multiband generations in the dielectric resonant antennas. So here these are my outlines. First we are going to be discuss about some small and very brief introduction about your DRA, and then I will discuss about your need of the multiband DRA and what the different techniques are available in the literature, so that by using those techniques we are able to generate the multiband characteristics inside the DRAs. And after that, I will discuss these 4 designs in which I have used these techniques which are available in the literatures and created your different kind of your multibands. So first, I will go for your dielectric resonant antennas. So as everybody knows that from last 2 or 3 days, we are going to lot of about your dielectric resonant antennas. So I'm not going to be in detail about the dielectric resonant antennas. So here I have given the brief history in these 2 or 3 different lines. The first I'm going to say that this concept of the dielectric resonators is introduced by Dr. R.D. Richmere in 1939. But this concept he has given, but he has unable to shown in its experimental verifications, because at that time the material technology are not up to the mark, so that he cannot fabricate that kind of their structures. So after 21 years in 1960s, the first dielectric resonators were practically fabricated and used for their oscillator and filter applications into their microwave circuits. And from 1960 to 1983, this concept is basically going to be used for their oscillator and filter applications. But nobody has thought about, can we use this concept for the antenna application also? So in 1983, Professor Long group has been first introduced this dielectric resonator for the antenna application. So that's why the name comes into the picture. Dielectric resonator antenna behave as a dielectric resonator behave as an antenna in place of their oscillator or filters. So that's why the name is dielectric resonator antenna comes into the picture. So what is the DRA? So here I can say that the DRA is a resonant antenna fabricated from low loss ceramics, so low loss ceramic materials. And if we are going to be compare the dielectric resonators and dielectric resonator antennas, there are the small differences into their properties of their ceramic materials. If you go for the dielectric resonators, you require very high dielectric constant materials so that the quality factor is going to be high, so that we are able to hold the electric field within the dielectric resonators, and then we are going to be enclosed the dielectric resonator by their metallic boundary, so that we can convert this dielectric resonator as oscillator applications. But when we go for the dielectric resonator antenna applications, in that condition, what we are going to do, we just lowering down their dielectric constant of their material, so that the property of their holding electric field is going to be reduced. That means we are able to provide the conditions so that the energy is basically going to be start leakage from their DRA itself. So that's why that is basically going to be work as an antenna here. So the main important concept of the dielectric resonator antennas to select the proper material for the getting their good results in case of their antenna applications. And here the resonant frequency of DRA is basically going to be the predominantly a function of size, shape, and material permittivity. So here this material permittivity is going to be create their important point. So whenever you are going to be design an antenna, first you have to focus on to their material permittivity or dielectric constant of their material, because that is going to be their prime factor to get their resonant frequency. And that is basically going to be used for the efficient radiator in microwave and millimeter wave frequencies. The reason is that this antenna is basically doesn't have any metallic structure, so there is no problem related to their metallic losses or surface wave losses. So that's why this antenna is going to be shows the very good radiation efficiency for the microwave and millimeter wave frequencies. Second thing is that due to dielectric in nature, that antenna is going to be have their higher power handling capabilities. So that antenna can be used for to their such kind of their application where they require their higher power handling capabilities in place of their microstrip patch antennas. So if you go for their advantages, so here I have listed some small advantages. The first is the high radiation efficiency, because there is no conductor losses due to the absence of their any conducting material inside the DRA, because in the DRA only dielectric material is going to be radiated. So that means there is no metallic structure, so no conductor losses. Then the safe flexibility, we can use any type of their safe which you are able to fabricate with the help of their electric material. And avoidance of your surface wave, which is related to there's no conductor loss. That means if there is no metallic structure, there is no surface wave. Surface wave is going to be present. So that's why this is another advantage. And this concept is going to be very important role when we are going to be design the dielectric resonator antennas for their millimeter wave applications or very high frequencies. In that condition, the surface wave is the primarily disadvantage into their microstrip technologies. And next is the basically easy to control over size and bandwidth. So here, as we know that the resonant frequency is going to be the function of their shape, size, and material permittivity. So by changing anything, you are able to control your bandwidth of your antenna. Again, if we are going to be go for your comparison, then we can say that this antenna is also having some disadvantages with respect to the printed circuits. The first is that the fabrication is generally more complex and more costly. Why it is like that? Because we are using your ceramic materials. So the construction of your ceramic materials is first is a difficult job. Second thing, the machining is basically going to be very complex, because the ceramic material is brittle in nature and they are very hard in nature. So the machining is basically one of your crucial job, and due to that, the fabrication is going to be difficult. So that's why the cost is going to be more. So that is a major disadvantage with your dielectric resonator antennas. But if you are able to have some good materials which are able to do the machining properties, in that condition, that problem can be solved. Second thing is that the design of resonant frequency as compared to their microscope antenna for its native hardness. So that is another disadvantage of your DRA in comparison with your microstrip patch antennas. So the basic shapes of DRA, if you are talking, then we can say that we are having the three important shapes. For the first one is the basic hemispherical DRA, second one is the cylindrical DRA, and last one is the basic rectangular DRA. These three are your most basic shapes in case of the dielectric resonator antennas. So if we are going to discuss about your hemispherical DRA, then we can say that in this DRA we are going to have your two different things. The first is the basically your radius of your DR, and second is the basically your dielectric constant of your DR. Clear? So here this DR is going to be offer 0 degree of freedom. 0 degree of freedom means if we are going to have same dielectric constant, that means if you are going to fix the dielectric constant value for the your hemispherical DRA, then we are going to have only one parameter, which is the radius of your DRA, to control the resonant frequency and quality factor of your dielectric resonator antennas. So that is basically your major problem with your hemispherical DRA. But with these problems, we are going to have some other advantages with your hemispherical DRAs, like the supporting of their fundamental modes and the radiation patterns that we are able to get it in case of your hemispherical DRA. Second one is the basically your cylindrical DRA. So in the cylindrical DRA, we are able to get your 1 degree of freedom as compared to their hemispherical DRA. So here you can see that if we are going to characterize your cylindrical structure, then we are going to have these two parameters. The first is the basically your height, and second one is the basically your radius. So here we can say that the ratio of your radius by height is going to play your lots of role to control the resonant frequency and quality factor. So here we can say that if you are going to make your epsilon r constant, as your dielectric constant, then by changing either r or h, you are able to control resonance frequency and quality factor. So here we are going to have only radius, but here we are going to have another factor, that is your h. So that's why here the antenna engineers is going to get their another flexibility in terms of their controlling resonant frequency and quality factor. Then the last one is the basically rectangular DRA. So in the rectangular DRA, we are going to have 1 more degree of freedom as compared to the cylindrical DRA. So total we can say that is a 2 degree of freedom. So 2 degree of freedom means, so here we can say that if we are going to have the cylinder rectangular shape, then we are having your length and width and the height of your DRA. So that means now here we are going to have two different concepts, that is the basic length of width and depth of width. So that means by changing any one dimension here, we are able to control the resonant frequency and quality factor. In case of the cylindrical DRA, we are going to have the two things, radius and height. But in case of the rectangular DRA, we are going to length, width, and height of the rectangular DRA. So to control your resonant frequency and quality factor of your DRA. So if you are going to see in terms of your designing flexibility, rectangular DRA is going to offer your maximum degree of freedom for the designers. Then the mode nomenclature for the cylindrical DRA. So here today I'm going to discuss about your cylindrical structure. So that's why I have considered here cylindrical DRA nomenclature. So modes into the cylindrical DRA. So in the cylindrical DRA, we are going to have the three different type of your modes. The first is the TE mode, then TM mode, and hybrid mode. If we are talking about your fundamental mode, so in case of the TE mode, the fundamental mode is TE01 delta mode. And if we are basically going to see the field distribution, you can find such kind of your field distribution. So TE01 delta mode, we can say that the condition is going to be your just like your electric dipole, so that we are able to get your such kind of your field distribution. In the case of your TM01 delta mode, so here you can see the field distribution. In this particular condition, the field is basically that the condition is going to be, we can say that here the field is basically going to be generated into this particular arrangement, which is known as your TM01 delta mode. And in this condition, I can say that the excitation mechanism is basically going to work as a horizontal, or we can say that they are magnetic dipole, so that we are able to get such kind of their structures. Then we are going to have your hybrid modes, where we are going to have these two fundamental modes, HEM11 delta mode and HEM12 delta mode. And the field distribution is basically shown here. That is going to be give your information about your electric field distribution. So in the case of the dielectric resonator antennas, the mode is basically going to be decide what kind of the radiation pattern we are able to get. So if we are going to be consider your TE mode, in that condition, the field is going to be your broadside. But if you are going to be go for your TM mode, in that condition, you will get your radiation field, which is going to be follow your omnidirectional pattern or monopole type of your pattern. In the hybrid modes, the field is going to be your broadside condition. But the difference is the TE mode and HEM mode. That means in the HEM mode goes, the direction of their maximum radiation is going to be coincide with their broadside. But in the case of their TE mode, we are going to be get some tilting with respect to their direction of their broadside conditions. So which mode you are going to be excite, that is going to be decide the kind of the radiation pattern you will get into the case of your dielectric resonator antenna. So whenever you are going to be decide any application, then you have to decide what kind of your shape you are going to be select for DRA, and then which mode you are going to be excite. Then I will discuss about the need of multiband antennas. So in the current situation, we can say that the single portable devices, for example, your mobile phone, we want that device is going to have the ability to operate into the different communication services simultaneously, like your Wi-Fi, GPS, Bluetooth, and etc. So in order to make it reality, we have the requirement of your multiband antennas. So then we can say that the statement which I have given above, that can be interpreted into a different manner. For example, let us suppose if we want to operate the mobile devices in different bands simultaneously, then it would be difficult to put the different antennas in single wireless device. It is because of their two important reasons. The compactness is the prime requirement of the modern communication system, and complexity should also be low. So that means if you are going to be put different antennas for different application, for Wi-Fi, for GPS, for Bluetooth, that means minimum you require 3 different antennas. So incorporate 3 different antennas into your single device. It means the size of your device is going to be increased, but our requirement is the compactness. So that means we have to design an antenna that is going to be support all these 3 services simultaneously. Second thing, that if you are going to be incorporate 3 different antennas, in that condition, the complexity of your designing is going to be increased, and due to that, the cost is going to be increased. So that the requirement of your multiband design is going to be your prime need into your today's wireless communication system. So that is the reason we are going to be focused on your multiband antenna designing in case of your portable devices or current communication technology. If we are basically going to be see the literature in case of the dielectric resonator antennas for the multiband application, then we are getting these 3 different techniques to generate your multiband. The first is the basically your use of multiple DRAs. So here, the use of multiple DRAs means we are going to be use more than one DRA in a single structure, so that each DRA is going to be operate or resonate at a different frequencies. So in that manner, we are able to generate your multiband performance or multiband characteristics. But the major disadvantage of this concept is that the compactness is basically going to be reduced. The size of the antenna is going to be bulky because you are going to be use more than one DRA into your single structure. Second is the basically your hybrid DRAs. So in the hybrid, as the name is suggesting, where we are going to be have your combination of DRA with other resonating structure. It means here we are going to be use more than one different kind of your antennas, so that we are able to get your different bands. So for example, in this condition, we are going to be have this ring shaped DRA, which is going to be operated with their own fundamental frequencies. Along with that, we are going to be have this patch structure inside that, which is going to be useful to generate that to provide your excitation for your DRA. but that is also going to work as a resonating structure, that is work as a antenna element here. So we can say that that is the basically your perfect example of your hybrid DRs, where we are going to have more than one resonating structure in one antenna. The third one is the basically multiple radiating modes, or we can say that the multi-mode generation concept. In this case, we are going to generate more than one mode inside your single DRA. So here, the beauty of this method is that the size of your antenna is going to be compact, because we are going to use single DRA, and here we are going to generate different kind of your modes, so that we are able to get your different frequency bands, which is going to give your multi-band performance. So now, today I will discuss these 4 different kind of your structures, which are based on to these techniques that is available into your literatures here. So the first structure that is shown here I am using your concept of your hybrid DRA. So in the hybrid DRA, that means we are going to have your combination of your DRA with other resonating structure. So what I have done here, I have used these 2 asymmetrical C-shape printed lines. One is the basically your smaller, another one is the basically your larger. And then I have used your 2 DRA, which is basically going to be put onto your one on the top of 2, but with some offset distance here. So why we put the offset distance, that is a different matter that I will discuss one by one. So first I will discuss about these 2 printed lines, and then I will see what is the performance with respect to your DRAs. And then I will see the effect onto this offset, so that we are able to analyze your complete performance of your antenna. So here I have taken 3 different cases. In the first case, when only large C-shape printed line is there. In the second case, when a small C printed line is there. In third case, when we are going to have your actual antennas. So here, if you are basically going to see, in all the 3 cases, we are able to get your different bands. So in the first case, when we are going to have the large C-shape printed line, then you can see that we are able to get these 4 different bands in case of this particular structure. But if you are going to see into your small C shape, then you can see that we don't have some of the bands in this structure, but we are going to have some additional band. And the third, that is your proposed one, we are going to have all the bands which are going to be combining with your first case and second case. But if you remember the last case, that is basically going to be constant in all the 3 cases. That means this case is basically going to be due to your dielectric resonator antenna, and the remaining is basically due to your either larger C-shape printed line or a small C-shape printed line. That is basically going to be resonate at different frequencies. So when I am going to analyze it, then I find that the lower frequency band, that is your 2.5 to 2.98 gigahertz, is originated due to your smaller C-shape, and these 3 band 1.25 to 1.35, 3.3 to 4.05, and 4.86 to 5.35 due to your larger C-shape. That means these 4 bands, first, second, third, and fourth, all these bands is basically going to be due to your C-shape structure, whether the smaller C-shape or larger C-shape. And the last one, that is basically your highest upper band or highest order band, that is basically due to your dielectric resonator antenna itself. So we can say that this is a perfect example of your hybrid antenna to generate your multi-band response. So here I have done some smaller mathematical analysis to analyze that whether whatever the things we are able to get from this as one curve, that is going to be correct or not. So here we are basically going to analyze this resonant frequency of your TM11 mode, and from that we can calculate the fundamental frequencies by using your following relations. So here, when I have drawn the surface current distribution at these 3 different frequencies, 1.45, 3.54, and 5.34. So when I am going to analyze these things, then I found that all the 3 modes into that larger C shape is basically giving the information about your TM11 modes, and these 2 are your first loaded mode and second loaded mode in the larger C-shape device. And when I'm going to see into the case of your smaller C-shape, then we are able to generate your half wave dipole mode in case of your smaller C shape. So here from the mathematical analysis, we are able to see that whatever the results we are getting in case of your simulation, they are basically going to be verified with respect to your mathematical analysis. Now, the larger, that is your upper sideband, that is at your 8 gigahertz frequency, when we are able to see the frequency distribution, that is a field distribution inside your DRA, then we find that we are able to generate the fundamental mode, T01 delta modes. And when we are going to go for your mathematical verification, then we find that the value is going to be your 7.45 gigahertz, which is the nearest to our simulated values. After that, we have gone through your analysis of your partial ground plane. So in the proposed structure, we are going to have your partial ground plane. So here, when we are going to increase this LG, then we are able to get that the length of your partial ground plane decreases and the impedance matching of the all resonant peaks created to your dual C-shaped lines becomes improved. So that partial ground plane is basically going to be improved, the impedance matching in all the resonant peaks, which are going to be generated with the help of your smaller or larger C-shaped structures. Now, the analysis of their offset distance. The offset distance means when we are going to be use two different DRA, and that is going to be placed one on the top of your another, and the top DRA is going to be shifted from your smaller DRA sides. So in that condition, when we are doing this analysis, because the DRA is responsible for this higher band. So here, when we are going to be increase this offset distance, then we are able to increase the bandwidth of that particular band, and this bandwidth is basically going to be increased due to your decrease into your effective permittivity of your overall Z-shape CDRA. Now, the analysis of their circular polarization creation. So here, in that condition, I have gone through your different cases of your proposed antenna. So when we are going to have case 1 and case 2, in that condition, when we are going to have either larger C shape or a smaller C shape, in that condition, we are not able to generate your circular polarization. But when we are going to have your proposed structure, so in the proposed structure, that means we are able to generate the dual orthogonal modes inside the CDRA by using the C-shaped printed line. And when we are going to be created your offset distance, due to that, the 90-degree phase difference condition within your orthogonal modes is going to be completely established. So that is the reason we are able to get your perfect circular polarization in case of your higher order mode, that is in case of your direct resonator antenna or DR band. So here I have shown your electric field variation in upper and lower CDRA with different offset distance. So this is 1.5, 2.5, 5 mm and 7.5 mm. So here you can see that when the offset distance between your upper and lower CDRA increases, the phase of E field line changes. So here we can say that we are able to control the phase by changing your offset distance, so that we are able to get your complete 90-degree phase difference between your two orthogonal modes, so that we are able to generate your circular polarization characteristics into your direct resonator antenna or the band which are going to be created with the help of your direct resonators. So now your experimental analysis. So here I have measured the fabricated structure and found that there is a very good agreement with respect to your simulated values. And also we are going to be say that we are able to get your 5 different bands which are generated due to your either smaller C shape or larger C shape along with your direct resonator antenna. So we can say that here this is the perfect example in the case of your hybrid techniques for generation of your multibands. Then the axial ratio variation. So you can see that we are able to create circular polarization into your band which is going to be generated with the help of your direct resonator antenna. That is your upper band, that is your 8 gigahertz band. So here you can see that we are get your good matching with respect to your simulation result in case of your axial ratio variation. and we have done this acceleration analysis into your broadside condition. Now the gain and radiation efficiency analysis. So here you can see that we are able to get your good gain and better than 80% efficiency in the throughout all the different band. And if you are going to be see, we are able to get your good gain in case of your higher mode, which is going to be generated by your dielectric resonant antennas. As we already know that the DRA is going to be offer your better gain in as compared to your microstrip antennas. Now here, these are the basically your different radiation patterns in the different bands which are generated in that proposed antenna structure. So all the lower bands is due to your printed lines that are the C-shape, larger C-shape or smaller C-shape, and the higher order band is going to be give your circular polarization. So here I have measured your LSCP and RSCP radiation pattern. Now the second design, in the second design here, I have used your cylindrical dielectric resonator antenna, and I'm going to be use this unique kind of your excitation scheme. So here I'm going to be see whether this particular kind of your excitation scheme is able to radiate or not. If it is not radiating, then we have to see that what are the different modes is going to be generated due to this specific or innovative design of your excitation scheme here. So here, this particular structure is giving your information about your multi-mode generation, because if we are going to be go for your analysis part, then we can find that this particular designed excitation scheme is not going to be participate into your radiation. That means only dielectric resonator antenna is able to radiate. So here we are going to be create a different kind of your modes inside the DRA, and each mode is going to be have their unique band, so that we are able to generate your multiple bands into your this proposed structure. And here I have shown your optimized dimensions of this particular design. So here the first is the basic analysis of your antenna. So here what I have done, I have used your one circular patch, and that is going to be energized from this particular port 1, and here we are going to be have the cylindrical DRA. And when I have seen the S parameter variations, then I will get these two different band. So in these two different band, when I have analyzed that with respect to your plotting the electric field distribution, then I find we are able to generate these two different mode, HEM1 to delta modes and HEM1 to delta like mode. So HEM1 to delta like mode, when we are going to be generate, then we seen that what are the necessary conditions so that we are able to get these two kind of the modes. Then we have analyzed that the circular patch is going to be act as a linearly polarized current seed, which provides all the suitable boundary conditions to get your HEM1 to delta modes. Second thing, that to get your HEM1 to delta like modes, then we have again analyzed that then the high current density at the edge of this circular patch, we are able to get this HEM112 delta like mode. And when we are going to be go for their mathematical variation, mathematical analysis, then we find that HEM11 delta and HEM12 delta mode is going to be generated at 2.28 and 5.32 gigahertz. So here you can see that we are able to get your 1-2 delta like mode at 5.1 gigahertz and HEM 1-2 delta mode at 5.630. So both modes is near to their 5.32 gigahertz. Now the creation of their another two band, that is your HEM11 delta mode and HEM11 delta plus mode. So here what we have done, we are basically going to be use the annular structure along with your conformal strip. So first I have used your annular structure and I have changed your diameter or radius of this annular structure, and then I will see what is the effect on that particular structure. So here you can see that when we are going to be change the radius of your dielectric, that is the radius of this annular strip, then you can see that we are able to get your better impedance matching. And when we are going to be put your one vertical strip along with this annular structure, we are able to get your another second band. So here we are able to get your two different band which are going to be useful to generate, or which are going to be created due to these two different generated modes inside your DRA. So here you can see that at the radius of your annular ring shaped interline increases, the impedance matching is going to be improved into your 6 gigahertz. Then the 2.5 gigahertz with your lower band is not very much affected with the increase into the radius of your annular strip. And the vertical strip is basically going to be improved, the impedance matching into your lower band. So from here you can see that the annular strip is going to be have their prominent effect onto this upper band, and this conformal strip is going to be have their prominent effect onto your lower band. So here if you see in the previous line, we can say that we have calculated the resonant frequency of the HM11 delta mode, which is the 2.88 gigahertz. So here you can see that we are able to generate the band that is near to the 2.5 gigahertz, which is very close to the HM11 delta mode. So to confirm the HM11 delta modes, we have drawn the electric field distribution at the 2.53 gigahertz at the resonant frequency of the lower mode and resonant frequency at the upper mode. So from these two electric field distribution, we are able to say that we are able to create HM11 delta mode at the lower frequency and HM11 delta plus mode at the higher order frequencies. So here we can say that we are able to generate these 4 different bands up till now in that particular structure. Now I am going to be combine all the feeding structure. That means the circular patch along with your annular and then your vertical strips. And when we are going to be do this analysis, then we are able to create another mode, which is the TM01 delta mode into your dielectric resonator antenna at your middle band near to your 4 gigahertz. So this band is basically going to be created to your coupling of your circular patch with your annular ring shape. And due to that, we are able to get your TM01 delta mode into your dielectric resonator antenna. So to verify we are able to get this band or not, we have drawn the electric field distribution, and from the field distribution we are able to say that we are able to generate the TM01 delta mode inside your dielectric resonator antenna. So here you can see that with the help of this modified design of your excitation scheme, we are able to generate 5 different kind of your modes inside the dielectric resonator antenna. And these 5 different kind of your modes is going to be give your 5 different kind of your field, 5 different kind of your, I can say that the bands into your S11 response. So here you can see that the lower frequency, the lower band is going to be due to your HM11 delta mode, then TM01 delta mode, and other 3 bands we are going to be get from your HM12 delta, HM12 delta like mode, and HM11 delta plus mode. But when we are going to be say that all these 3 modes are very closely to each and every one, and due to that the mode merger is going to be happen here, so that in place of these 3 separate bands, we are able to get your one wide band in case of this particular structure. So we can say that the mode merger techniques is also going to be used to make the structure wideband. So here, if you want to go for your multiband generation, then you have to choose the fields, we have to choose the modes which are physically separated to each other, so that we are able to get your 3 different or 4 different bands. If they are very near to each and every one, then the mode merger concept is going to be comes into the picture, and we are able to get your wider band structure or wider band response. Similarly, we have seen your gain and radiation efficiency of your antenna. Then we can find that the gain value is lesser into the 3.5 gigahertz as compared to another one, because in the 3.5 gigahertz we are going to be get the TM01 delta mode, and we have analyzed the gain into their broadside direction, and TM01 delta mode is going to be have their monopole kind of your radiation pattern. So that is the reason we are going to be get your minimum gain value into that particular band. Now the far field pattern. So here I have measured the far field pattern into your XZ and YZ plane. So you can see that in the 3.4 gigahertz we will get we are getting the TM01 delta mode, which is going to be your monopole type of your radiation pattern, and remaining mode is going to be have your HM1. So they are going to be have your broadside radiation pattern. So whatever the bands, whatever the modes you are going to be created, they are going to be reflected their radiation pattern. So from here we can clearly see that we are able to generate these different kind of radiation pattern with respect to different modes which are created here. Now, if we are going to compare the performance of both antenna design with respect to available structure, then we can say that the first antenna is going to give their dual response. That means linear along with their circular polarization. And here we are able to get their 4 band. In the antenna B, we are able to get their 5 different band. Now the design C. In this design C, we have used your innovation into your feeding structure, especially this aperture design. And due to this aperture, we are able to get your multiple bands into your structure. But this aperture is basically going to be provide the necessary condition to excite your multiple mode inside the DRA. So we can say that this is an example of your multi-mode generation or multi-mode creation into your dielectric resonator antenna. So here I have given your physical insight of your antenna. So we can say that first step, we have designed your one circular aperture, and on the top I have put your one cylindrical DRA. In the second condition, I have cut your one slot, that is your plus shape, into your microstep line, and then I have incorporated your one L-shaped structure, and after that I am going to modify this circular patch or circular aperture into your DRA. So when I have done this analysis and see your S11 response, then I find that I am able to generate 6 different bands into your dielectric resonator antennas. So here we can say that we are able to generate 6 different modes in the DRA due to this particular type of arrangement. So first I have to identify whether these modes due to these peaks due to their 6 different modes into your DRA, or is there any possibility so that this aperture is basically going to be radiate. In that condition, the antenna is going to go into your hybrid concept. So here I am going to analyze whether these 6 bands is created to your 6 different modes or not. So for that purpose, I have drawn the electric field distribution inside the CRA at each and every peak of your 6 different band. So first band is the basically 1.1 gigahertz, and in that condition I have used this empirical formula to get your values. When I have drawn it, then I find that the HEM11 delta mode is going to be generated at their 1.2 gigahertz. And when I see the field distribution, then it is going to be confirmed that at the 1.1 gigahertz we are able to generate HEM11 delta mode. Then I have shifted to the second band, which is the 1.5 gigahertz. And when I have drawn the field distribution into the 1.5 gigahertz, then I find that this field distribution is just like the HEM11 delta plus one mode, or HEM11 delta like mode. So that is basically going to give your clear-cut idea about your second mode which we have created. And then I have calculated the resonant frequency of this particular created mode, and I found that the value is going to be your 1.5 gigahertz, which is the exactly same value with respect to our simulated analysis. So we are going to confirm that we have created HEM 11 delta plus 1 mode at the 1.5 gigahertz. That means the first 2 peak is going to be generated due to the HEM11 delta mode and HEM11 delta plus 1 mode. Now I can say that it is going to be confirmed we have created these 2 bands, these 2 modes which are responsible for your generating first 2 bands. Now I have go for your next condition, where I have to see the HEM113 delta mode. So when I am going to use this mathematical expression for calculating the HEM113 delta mode, I found that is basically a 2.65 gigahertz. Then I have analyzed all the field distribution at the different peaks with respect to our S parameters. So I found that I am able to generate HEM1113 delta mode at the 2.3 gigahertz, which is very close to our theoretical analysis. And from your field distribution, it is going to be confirmed that we are able to get your HEM13 delta mode here. So here we can say that the remaining three frequencies 2.04, 2.4 and 2.6, when we have analyzed that, we are able to get your HEM12 delta mode and HEM14 delta modes. So here I can confirm that HEM12 delta like mode, then HEM12 delta, HEM13 delta and HEM14 delta mode is going to be created at 2.04, 2.3, 2.4 and 2.6 gigahertz. So here we are going to be confirmed that all the 6 peaks which are generated in the S11 response of your proposed antenna are due to the generation of your different 6 modes inside your dielectric resonator antennas, and all the modes are the hybrid modes. So one important analysis from this one, that the hybrid mode is going to be have your similar kind of the radiation pattern. So here we can say that we are able to get able to maintain the consistency into the radiation pattern due to the creation of your similar kind of your modes inside your DRA. Now the second analysis is the basically examination of your CP wave. So for that purpose, I have gone through the again of same different step procedure to design this particular antenna. Then I see that due to incorporation of this small L-shaped strip, we are able to get the circular polarization into your first 2 band of your proposed antenna. And when I am going to be modified this circular aperture, then we are able to get your another 2 bands, that is your impedance matching is going to be your improved. Due to that, another 2 modes is basically going, another 2 bands is going to be get your circular polarization. And here I have shown your variation of your L1 and L3 length, which is the basically your this length and this length, that is your L-shaped structure length. And then we are going to be say that this particular L-shape is going to be responsible for getting the circular polarization into this particular structure. Now I have fabricated this structure and measured it. Then I found that I am able to generate these 4 different bonds, which is going to be have your 6 different modes are going to be energized here. But again, you see that HEM12 delta like mode and HEM113 delta and HEM12 delta are the very near mode, very near one. So that's why the mode merger techniques is going to be implemented here. So we are able to get your one wideband structure. Otherwise, we are able to get your 6 different band due to their 6 different modes inside the structure, but they are going to be very closely to each other. So that's why we are going to be get your one wideband response into that particular band. Similarly, we have calculated that we have measured your axle ratio and gain. Then I found that we are going to be get your 4 circularly polarized band into this particular structure. So we can say that we are able to generate quad-sense quad band structure, which is unique in their own kind into the antenna literature. Then the far field variations here, you can see that we are able to generate your HEM11 delta mode or all the HEM modes. So you can see that the broadside pattern is basically going to be come to the picture here. Now the performance comparison. So here you can see that we are able to generate your 4 different bands. Similarly here, we are going to be get your 4 different bands, but here the sense of polarization is quad as compared to your another published structure. So that is going to be your unique in case of your dielectric resonator antenna. Now the last design is basically your antenna 4, where we are going to be use your similar kind of your inspiration which we have designed into the previous antenna. And here I have used this size set structure along with this conformal strip to generate your different modes into your dielectric resonator antennas. So here you can see that is the basic designing procedure. From here we can say that we are able to generate your HEM11 delta mode into your cylindrical DRA. And then I have gone through your further analysis. Then I can say that in the upper side mode, we are able to generate your HEM11 delta and HEM12 delta mode. And here, when we are going to be verified with respect to your mathematical analysis, then we can say that it is going to be your perfectly matched with respect to that particular analysis. And when I am going to be your final antenna structure, then we are going to be getting another peak. And this peak is due to your TM01 delta mode. And that is the basically your due to the addition of these two small C-shaped structures, so that can get your psi-shaped structure, and that is going to be create your virtual electric dipole. Due to that, we are able to get your TM01 delta mode. So when we are going to be verify with respect to your theoretical analysis, so we can say that is going to be confirmed that this particular band is due to your generation of your TM01 delta mode. So when I am going to be see the comparison of the simulated and measured result, then I can say that they're able to get your three different bands due to your three different modes inside your DRA, and each mode is basically going to be have their own characteristics and own band. So here we are able to get these three different band into your dielectric resonator antennas, and here you can see that the TM01 delta mode is going to be have your lowest gain, because I have measured this gain into the broadside direction, and we know that TM01 delta mode is going to be give your monopole kind of your pattern. So that's why in the broadside we are going to get your lower gain. But if you go to the another sides, we are going to get your better gain in case of your TM01 delta mode. And here you can see that is the pattern of the TM01 delta mode, and remaining two is the basically going to be give your HM mode. So here, if we are going to go for the conclusion and feature scope, then I can say that I have presented 4 design. The first design based on their hybrid techniques, and remaining 3 design based on their multimode generations. So we can say that the first antenna is operated into their 4 different bands, and also showing their one circular polarization into their one mode. Second antenna is the multi-band structure, and due to their multi-operating bands, where we are going to be generate your 5 different kind of their structure. The second, that is the third antenna, where I am able to generate their 6 different kind of their structures, 6 different kind of their modes. Due to that, we are going to be get their quad band and quad circular polarization characteristics. And last antenna is going to be have their triple band structure, where we are going to be get this triple band due to their creation of their these triple modes into their antenna. So what should be your future scope of this multi-band structure? So here we can say that the multi-band characteristics can be generated by creating some new type of the radiating model pattern inside the cylindrical DRA, like HEM13 delta mode, 14 delta mode, TM01 delta mode, or another higher order modes, which we have not explored up till. So you are able to design some unique kind of their excitation structures. Due to that, we are able to provide all the necessary condition to generate these higher order modes. And if you are able to generate these higher order modes, that means you are able to create your multi-band structure. Or we are going to be go for their combining this multi-band structure along with their compactness, which is another aspect of their future antenna research. Or I have used the completely cylindrical structures. You can go for their another shapes where you are having the advantage of their lower Q factor, so that you can get their better response. Or you can go for their MIMO structure, where you are going to have their multi-band response. These are the applications related to these papers, these structures which I have shown, and here are the references. Now, thank you very much. If you have any question, then let me know.
Thank you, Professor Gangwar, for your nice delivery of informative contents. Here are some query on the lecture. What is the setup frequency for dual band DR designs?
Setup frequency.
Yeah.
So here I have not gone for the dual band structures. I have gone to the triple or quad band structures, where my main focus is that I'm going to generate these their creation of their different kind of their modes. So here I'm going to be focused on their excitation scheme, not on their DRA parts, how we are going to be analyzing. So that's why I have created these conditions. But if you are going to go for the dual band structures, then the previous expert, Professor Leong, has given your complete detail about your dual band response, how we are able to go for the calculation, complete mathematical analysis. So you can refer those slides for the dual band designing.
Okay. Like multi-band or higher modes can be excited by following the path of TE, HE, HEM. Which one is best approach as far as design, fabricated design is concerned? We need to proceed for TE, HE, or HEM for exciting higher modes.
As per my experience, I can say that the excitation of your hybrid modes, higher order modes in the hybrid structures is easy as compared to your T or TM modes.
Okay. With this, thank you very much, and thank you for being with us and giving two different lectures. With this, I must say final bye-bye to Professor Gangwar, and let us welcome our next speaker, Professor Bhaskar Gupta from Jadapur University, Calcutta.
I'm here already.
Yeah. Yes, sir. You please share. You please share your screen
Right.
first. Then I will proceed
Yeah,
for.
right. Share my screen. Yeah.
Yeah.
That's what I was going.
Okay.
Right. Just a minute. Where is that?
Bottom right corner. There is an option of present now. Bottom right corner.
No. Is the phone report present now? Yeah. Sure. Your entire screen, right?
Yeah.
That's what I'm doing. After that, let you see my screen. Can you see my screen?
No. You click on present now, then select entire screen.
I just did that. Okay, I'm doing the same thing, cancelling and doing it again. Present now, show entire screen, and then there's this small window coming where the share the button for share is not activated. I don't know why. Don't want to share the contents of your choose what you would like to share. Okay, I have to do it. It seems I have to do it. Right. Let me see. Entire screen is not giving you the.
You open that present.
Okay. I'm just opening that.
Yes.
That's what I'm doing now.
Yeah.
So that I think if that's visible to you, then that will be all. Right. Give me just 2 minutes.
Yeah. Sure.
That's it. Can you see the screen now?
No, sir. It is not coming.
It's not coming this way. But my screen is showing the slideshow. Not yet.
No.
I don't understand this. I shared my screen. I presented and I shared my screen. What's happening? I don't understand. Let me check that again in Google. Well, sharing the screen. Something. Well,
Sonic Kiran, will you guide Professor Bhaskar?
Sir, entire screen. Not should I present a window? Window.
Sir, you can present the entire screen, no problem.
That's what I did, but you know what happened? I'm presenting the entire screen. What's happening is then I get a small screen here, which is the same thing. But then
sir, in the small screen, you just in the small screen you just click on the picture where it is showing the screen.
Okay.
The reference screen.
Okay.
You click on that, then you click share.
After that only share.
Yes, sir.
Well. The share was activated after that only.
Yes.
So now
Now you can. Now you can open the presentation.
Yeah. Now I go to the presentation and open it. That was not being activated because I didn't click on this part. Is it okay now?
Yeah, it is okay. Sir, bottom side 2 icons are there. Then you close. You are presenting to everyone. Close this one and then hide the second icon.
Oh.
Bottom side, sir.
So I go back there. I had already this thing on the screen. I go back to.
No need to go Bye.
No need to.
Yes, sir. You just open that one.
Yeah, I opened that one. Yeah,
PPT. Yes, yes.
yeah.
Okay.
Again, I'm doing that.
Then slideshow.
Slideshow from beginning.
Yeah. Okay.
I think
Now
it
you
should be
see
open.
on bottom side there is one icon.
Oh, stop
Stop
sharing.
sharing and
I.
hide.
Yeah,
You
yeah,
just
yeah.
you click on hide sharing.
On hide,
Yeah.
hide.
Yes.
That's it.
Yes.
Definitely, if
Yes.
it's a
Yes. Now it is
software,
good.
it should be hide.
Yes.
Okay,
Yes.
everything's okay
Okay.
now.
Yes.
So I think
After 1-2 minute interruption, we have
okay,
finally
okay.
come to the desired
But
things.
problem is we were already late in starting and schedule itself
No
was
problem.
delayed.
No problem. So
Anyway,
that
still
you can
better,
manage.
uh,
Yes.
better late than never.
Yeah.
So
Sure.
I won't waste my time on elaborating on the topic today. You
Okay.
see, it's already written on screen. Research on dielectric resonator antennas at my
Okay.
university. That's my lab. Now, about DRAs, I think you have heard quite a lot, but still, this presentation was just arranged in this fashion, starting with the introduction. Then you can see all the different sections through which we'll move one by one in due course. So I start with the introduction. Firstly, what is the impetus behind this research? We'll discuss that a little bit in brief. Then we'll shift our attention to mainly three application areas: development of wideband DRAs, development of multiband DRAs, and development of configurable DRAs for today. After that, about this application oriented research, we'll put some conclusions, followed by our list of publications, so that if you have any further query, you can consult them. Actually, today I'll confine myself to this application oriented research experience of ours. Tomorrow, I'll go to the more fundamental research and our publications therein about the theoretical aspects of the DRA structure, various forms of DRA structures. About today's business, let's first start with what was our impetus? Why did we take up? Why did we pick up this research at all? All these things again require no further discussion. Obviously, into increased multimedia applications has led to the demand of not only high, I would say, extremely high bandwidth. So something is to be done to generate antennas capable of operating at the higher end of the spectrum with consequently with quite high bandwidth. So we have to do something about this. There are two ways usually. Either we design antennas which possess wideband characteristics, as was shown. I can show that typical wideband antenna characteristic. See, the reflection coefficient is below -10 dB, which is an acceptable level, corresponding to VSWR equal 2:1 on the feed line over quite a wide frequency. This is a wideband characteristic. Otherwise, we can also design an antenna having multi-band characteristics. As much as I have heard of the last lecture, towards the end, there are also discussions were being made about that multi-band antennas, that type of multi-band DRA. See, this is a typical reflection coefficient or return loss versus frequency plot for one such antenna. And one other way is obviously the best amongst all these. That is to design antennas, we can dynamically alter its characteristic. You see, if we vary some parameter, here in this figure, the parameter was some applied voltage. This is using a MEMS type of the feed line incorporating MEMS, where by varying the actuation voltage, we can vary the total characteristic. So what are the recent advances in this regard? Well, you see, combine multiple resonators like a monopole antenna, a microstrip patch, plot to achieve multiple or wide bandwidth. Wide bandwidth will be achieved from multiple band antennas when the bands will be brought sufficiently close to each other so that, like the principle of staggered tuning, you'd be able to cover the two bands would merge and you'd be able to cover a large bandwidth. So I think we should rather now discuss about the problems still remaining. What are the problems? Well, the most fundamental problem is difficult to achieve wide bandwidth over multiple bands. In fact, multiple band antenna, multi-band antenna is always a requirement because at different bands there can be different type of application. But in each of those bands we require wide bandwidth. So what's the way out? Actually, DRAs showed us a way out amongst all the miniaturized, that is, miniaturized antennas. The miniaturized antennas research was started with microstrip. DRAs showed us in terms of broadbanding one step forward. I think all these are already known to you. That Richmeyer's work in 1938, 39, way back, it laid the foundation. But Long and Shen in University of Houston developed the first resonant DRA in 83 only. So late after that, after the first cylindrical DRA was developed, other shapes like hemispherical and rectangular were also developed, and they all radiated broadside. Well, you see, rectangular had 3 degrees of freedom, hemispherical 1, cylindrical 2. So we had different types of design, but nonetheless, this itself was a great leap forward in antenna technology. This was the greatest development after the development of microstrip patch antennas, ushering a new antenna completely. Before the work of Long and Shen, people just thought that the resonators are meant to store energy. They can't radiate. They can't radiate. So how do we use them as an antenna? But Long and Shen showed that under certain conditions, certain modes are generated which behave as leaky modes, not leaky modes in the conventional sense, but leaking energy that is like a leaky cavity. That is, it generates resonant antenna, DRA. Well, so for its analysis, an approximate model may be provided, which was actually the model used for at first by them as a leaky cavity. So we'll also take up that approach, but maybe tomorrow. Today I said it's more of application oriented antennas and application oriented research. But you see, these are meant to overcome the shortcomings of microstrip antennas, one of which is, of course, narrow bandwidth, as we discussed, and low power handling capacity. Not only that, because these are not using any metallic region, metallic portion, it's free of conductor loss, which is the biggest culprit in terms of loss collection. And so with this background, I think you have already been introduced to the shape and structure of these antennas, which I shouldn't dwell any further time on. Here are some examples in the figure. So this was the situation. At this situation, we started our researches quite a few years back. We wanted to develop, already have shown there, all those approaches. We wanted to take up all those approaches. We wanted to develop wideband antennas, we wanted to develop multi-band antennas, and we wanted to develop reconfigurable antennas. In terms of wideband, we took up two approaches using two shapes. We developed some rhombic antennas and some fractal based antennas. Fractal provides us with a very interesting situation to which we are coming presently. So, what happens at this topic? What happens is that now developed, we now devoted all our antennas to these. Let's start with the rhombic antenna. Well, the antenna here is placed on a metallic ground plane on which you can see a CPW. Look at the structure on the left. The CPW is meant to fade the antenna. Usually, all the DRAs are are just mounted like that on the ground plane. They are not left aside in free space, but that doesn't contribute to conduction losses, because essentially the field is confined in the radiator. But we have to do that for mechanical stability, for mounting purpose. It can actually be modeled as another equivalent structure, double the height, by removing the ground plane, that is considering the antenna along with its image. So you see the structure, and now look here what is the basis of design of this structure. This structure, as I explained, is fed by an inductive slot. Depending on the length of the slot, we can manage it to behave as inductive or capacitive or resonant. These are inductive slots. And DRA usually rectangular is a very commonly used shape. That rectangular DRA is rotated now around the vertical axis. So what happens? After the rotation, you get orthogonal modes excited along both principal axes of the structures. Then we subsequently tune those orthogonal modes, so that, once again, I told you at the very beginning, the very fundamental principle of getting a wide bandwidth is to merge closely spaced modes. So if these orthogonal modes can be tuned properly, we can get wide enough bandwidth. The work was done and published in the reference shown below in International Journal of Electronics. You see the E-field configurations corresponding to different rotation angles, showing how the two orthogonal modes are generated when the structure is made to occupy a rhombic position. And by simply following this technique, which is quite simple but quite innovative, we could get indeed a wideband characteristics, as shown by the S11 characteristic here. Here we have in the plot for the rhombic DRA, the measured S11 plot, and for the square DRA also, we have superimposed the measured plot. For both of these structures, we have shown the simulated plots by HFSS and Microwave Studio of CST. You see the simulated plots are tallying quite closely with the measured plots, indicating very little scope of error, and we can see very clearly how the two modes are merging, so that the square antenna is eventually being converted to uh, wideband antenna, broadband antenna. For the resonant frequency, you see for the square band, we get two resonant frequencies at 5.48 gigahertz and 6.20 gigahertz simulated. I think I better go to the measured result, because that is more precisely presenting what actually happened. For the square DRA, we get the two frequencies at 5.37 and 6.21 gigahertz, so that we can operate it there. Well, the two frequencies were shifted a little. You see, 5.37 had a much greater shift to 5.60 gigahertz, whereas 6.21 gigahertz frequency shifted to 6.25 only. In a simulated form, there's little change from there, but the shift of the upper frequency is even less, for the lower frequency is even more. Whatever be the case, in between these two frequencies, we get the bandwidth as shown for the square bandwidth, while the bandwidth over which it can be operated, that is over which we would get VSWR less than 2 is to 1, or in terms of S11 reflection loss less than 10 dB. You see, whereas the square antenna, in terms of the measured figure I'm saying, was providing us a 10 dB bandwidth of 440 megahertz only, it increased more than three folds to 1470 megahertz, almost 1.5 gigahertz, as is shown by the plot also. Was it radiating properly? Yes, it did. These are the plots at the two radiating frequencies, two resonant frequencies rather, 5.6 and 6.25 gigahertz. It's radiating throughout. And in order to understand the radiation characteristics, we investigated all the radiation parameters like gain, beam width, directivity, everything. You see, I am referring to the measured data only. The table clearly establishes that the measured data is quite close to the simulated data. Gain was at the two frequencies 5.5 and 5.3 dBi respectively, not bad at all, quite good. The 3 dB bandwidth in a phi 0 plane was 58.7 and 70.7 degree. In phi 90 plane, they were the corresponding figures are 70.6 and 70.5 degree respectively. And the cross polar discrimination, you see here you'll be surprised to get such a good, such a nice value. Cross polar discrimination was measured. I'm not talking about the simulated value. I repeat, measured at the two resonant frequencies at 30 as 38.9 dB, as high as that, and 23.5 dB respectively. In phi 0 degree plane, in phi 90-degree plane, the corresponding figures were 26.6 dB and 23.6 dB. That means always greater than 20 dB. The phi 0, phi 90, all of them were corresponding to this geometry as shown here in terms of x and y axis. So I go back to where I left this research. I believe here. So then I go to the broadband DRA development using the fractal concept. What is a fractal? We know that fractal has got self-similar properties which you observe in snowflakes or leaves. And nature is very fond of, they are very, very fond of fractals. Fractal literally means just fractions, broken shards, broken pieces. But do nature prefer broken pieces? Irregular broken pieces? Not at all. The breakage is always in a regular fashion so that you get the self-similar properties and self-generating properties. You get one iteration to another, very interestingly, similar type of structure, repeating and repeating, giving rise to fantastic figures. Like, you have heard of this definitely. Snowflakes and leaves and in many other examples, as I said, in nature. So here, what did we do? We had one fractal DRA. Well, before us, there were some activities on fractal patches, but probably we started first investigations on this type of fractal DRA. And this DRA was again fed by a CPW slot loop. You see, that is in fact the easiest way to feed these. Although they can be fed in many different ways, you must have come across that going through all the lectures in all these days, the different types of feeding. But we prefer this because it was easier for us to design and to fabricate and to control. This work was eventually reported in IEEE Transaction Antennas and Propagation. Reference is given at the bottom of this slide. Let's see the results what we obtained. But before that, what fractal we took up, we adopted for this particular research and how it showed through its structure, its shape, through different iterations. Every fractal has got a so-called initiator, where from we start. The initiator shape here for the particular fractal known as Minkowski Island fractal was a simple rectangle. From there, you remove some rectangular areas again to get a first iteration as shown. In the second iteration, you repeat this process in whatever is left with you. So you see, you get the second iteration. So from the initiator, You then use the generator on the initiator. Generator is this scooping out, cutting away of some indentation. In the generator, you can readily identify the indentation width. Then you go on repeating them from one iteration to the next, then to the third one, third, fourth, as much as you like. Provided, of course, you can fabricate it. And always in every iteration, you can change the indentation factor. Indentation factor means the ratio of this indentation width to the total width, or you can keep it the same also as you like or as is convenient to you. We have made some key observations on this particular structure. They're enlisted here. Uh, with increasing iteration, higher order modes are brought closer and closer. Well, lo and behold, that's the key to obtain wideband response. So we try to tune them to achieve that goal. Why? Because with increasing iteration, the resonant frequency shifts to the right, but larger shift for lower order modes, higher shift for higher resonant frequencies. That's what eventually causes. Just in the other case also we saw this, but of course here we expect in a fractal more such resonant frequencies because of this self-similar property, which can be mathematically analyzed in terms of so-called fractal calculus, where the dimensions are considered to be fractional. As I said, I'm not showing the mathematics today at all. That I keep aside for tomorrow. Today I'm just representing some application-oriented research with the results suitable for application. So take this one. Take this Minkowski fractal. First iteration, second iteration. This is the surface current distribution, electric current Js, of course. And this is the S11 plot. What happened to the conventional patch? Had there been a conventional patch? Just see the one simple line straight like that, and then that is showing a dip that's corresponding to a resonance much high, much above these resonances. And also here, because of dielectric nature, we would expect some magnetic current. Of course, that's hypothetical, just to model a slot, and that magnetic current distribution can be plotted like this. Similar observation can be made from here also. This look at this S11 plot. So that actually serves our purpose. That way only we can get our broadband antenna using this Minkowski island fractal. This is the structure of the after the first iteration. In this case, you see the look at the indent. The length is L by T and the width is I into L by 3. Why L by 3? Because the three segments here, one indented and the other two non-indented, all are equal, so that the gap, the indent can be pushed symmetrically inside. And I is that factor, as I explained, indentation factor. With this, and of course, with the other dimensions as shown in the figure, we developed some design formulae. First, going through theoretical calculations, then through semi-empirical approaches. I'm giving you only a final results because today I'm committed not to bore you with theory at the end of the day. That will be reserved for tomorrow. See, if we now calculate this factor Q, like the Fillion factor of microstrip, then the effective dielectric constant, you obviously know the concept of effective dielectric constant, so that everything like fringing and inhomogeneous nature actually is taken into account, so that the structure can be considered as effectively a homogeneous one supporting TEM modes almost. So the epsilon effective is, of course, as the definition of the feeling factor goes, just like microstrip, Q into epsilon naught corresponding to AF plus 1 minus Q into epsilon R corresponding to the dielectric of this antenna. That is as if by this factor the airspace is filled up. Now how to calculate this Q? By using that formula which we thus proposed. 2I delta square I is the indentation factor and delta is just shown here into a summation n is to k1, k is equal by n is to 1 to k being the number of iteration, delta to the power n minus 1 into a by b plus b by a, the aspect ratio seen in one way and in another way. And you see, this is corresponding all these just like for any DRA, in the rectangular case, we can consider the TM, Mn into this is into Mn delta, that is 1 0 deltas, and delta means just the mode number along the vertical side. Kx, Kz, they are given straight away like this. But talking of the other one, Ky, you can use the separation equation to get that. Delta here is that case, sorry, delta here is in this case is L by 3, that is the width of the slot divided by the total width, that is L by 3 divided by L, 1/3. Well, it doesn't correspond to that delta of the mode number, that corresponds to the number of half cycles along the vertical side. Anyway, so after that we can calculate the resonant frequency using these. So these can be used for design of the structure as well. After the first iteration, we get the computed resonant frequencies as shown with different indentation factors and the simulated values again as shown, so that we could check are we in the correct direction or not. We found that the error percentage is always within our control. Particularly when indentation factor is getting bigger, say from zero point 0.3 to zero point 0.5, error percentage is also reducing. So this was about Minkowski fractal, but many other fractal geometries also are there, like say Koch inner fractal. Koch inner fractal, you see the at the bottom, these are the structures after first and after second iteration, and correspondingly the S11 variation is plotted just above that. This Koch outer fractal, see, in case of inner fractal, indentations are in. In case of outer fractals, they are moving out. But I must appreciate the beauty of these fractals. This is a Sierpinski, very well known fractal. Sierpinski gasket. In fact, there are so many Sierpinski gaskets, Sierpinski carpet, all those. But the point is how to tune the fractal parameters to obtain the discrete multiple bands or broadbands. One problem is always there to generate multi-band antennas from these. Broadband antennas are rather more easy. Why? Because the relatively low Q factor of DRAs tend to merge those multiple bands together. What would be the effect of low Q factor? Low quality factor means at every band, the curve will be flatter, covering a wider frequency range. So eventually the multiple bands will definitely tend to merge. And then what did we get? From these studies, we found that variation of indentation length or fixed indentation widths is also an important factor. We varied indentation width for fixed indentation length, showed you the results. But if we do the reverse, that also is an important way to control its behavior. These are the results. We have varied the indentation factor by changing the indentation width only, keeping the indentation length the same. Again, taking up the same Minkowski fractal, you see the first iteration, second iteration would have produced a structure as shown. These are the field structures, and with different indentation factors, that is, with different indentation widths, we get these figures, as you can see. So after second iteration, we get this type of behavior. We can clearly see the bands. Only thing is that the bands have to be kept sufficiently narrow such that we get correspondingly multi-band operation. You see, that's what we succeeded in tuning the antenna performance by changing the indentation factor by once again changing the indentation width, keeping the indentation length same. As a result, this is something which you observe. After first iteration, the second resonant frequency vanished totally, was not observed. But after the second iteration, we got two clearly, but the two was separated by an amount large enough so that get a multi-band behavior, not a continuous wideband one. See, the resonant frequencies were then at 6.59 and 6.34 gigahertz. Of course, here the frequencies have been shown in a manner reverse to what we showed earlier. First the higher resonant frequency, then the lower. But you see that both frequencies, these are the simulated bandwidth and measured bandwidth, clearly visible, 2870 and 3380 megahertz respectively. Shouldn't we consider it large enough? Yes, of course. That means we have now solved a very interesting problem which is still as yet unsolved, to get a multi-band antenna with broad bandwidth both at both bands or more than two bands. Here only two bands. For more than two, well, we have to go for higher iterations, but that would consequently make the fabrication more and more difficult. These are the radiation pattern at the two resonant frequencies, three resonant frequencies in fact, and this is the corresponding gain versus frequency plot. Shows that the gain is always at a minimum about 3 dB and at a maximum about 5 dB, means within 2 dBi rather, gain margin. And again, radiation characteristics are tabulated here. See, as I said, the different values, I'm not reading out again. And of course, simulated and measured values are tallying quite well, excepting one or two few exceptions, but the measurement also might have been in error. And I must say that the cross polar discrimination is always nice, excepting that 7.43 gigahertz. But even then, there also it's above 12 dB. It's 13.2 dB. And how much do you get from a normal patch antenna? Say 10 to 12 dB. So isn't that good enough? Of course, for most of our world. So we have really developed multiband DRAs, multiband DRA with large bandwidth in every band by designing and by developing this dielectric loaded fractal loop antenna or DRA fed by fractal loop. You can view it either way. So now comes our next task, that is development of multi-band DRAs. Well, we did that. No, sorry, this is this work was presented in IEEE transactions and test propagation. You can see the fractal loop. Well, very interesting. This is just the other way around. Fractal loop to feed. Okay, not the dielectric. The dielectric is pure rectangular, but the loop is fractal. So that's why we rather consider this time we are sure the radiation, and we theoretically also established that is from more from the loop than from the dielectric. So we considered it as a dielectric loaded fractal. Well, you see, these are the surface current plots for different equations, and correspondingly the different S11 plots, surely showing a multiband behavior. Well, radiation characteristics are also shown here for both co and cross pole. The gain is also plotted. Gain, of course, obviously, is not that high for this particular antenna, but I believe for applications like like Wi-Fi nodes, like connected to WLAN, or for imaging applications, is enough, good enough gain. So you see, basically what's happening? DRA is placed on the top of the fractal loop so that we get a hybrid antenna, and the antenna characteristics are changed. So we study the change in the antenna characteristics as depicted here. And this, of course, is what we needed, a really multi-band antenna with many bands. And only thing was that now again we needed to develop a design formula. So this is what we developed for the resonant frequency, the structure, all the dimensions. This is the formula developed by us with the different factors modified as these. F naught is the fundamental resonant frequency. Fn is the nth resonant frequency corresponding to F naught, that is obtained this way. Well, empirical constant means that filling factor for the three different permittivity cases studied with if in every case two different values of perimeter of the slot loop. Well, these are the simulated, and I'm sorry, the units are not provided. Perimeter is in millimeter, 60 and 100, and the frequencies are all in gigahertz as before. Other two things, epsilon r and q are of course dimensionless. Resonant frequency, you see, if we computed means of course computed by us from our theoretical calculation, and then after that by fitting it to this formula which we developed. So you see, these are the results which validates our design formula also quite well. But we did not stop there. We tried to get to find out an equivalent circuit model for its proper analysis. The distributed transmission line, for that matter, any distributed transmission line segment can be modeled like the first figure. Now for the CPW fed slot line, see that to then have this particular structure for the stub, the portion below, and for the slot, the circuit segment above. Stub means feeding stub, so that you get the total equivalent circuit, and this is the result as you get from that circuit model through circuit simulation. Compare it with full wave simulation, you get a resonant frequency at same position, maybe a little bit of difference in magnitude, but full wave simulation, circuit simulation providing us almost the same results, validating our of our equivalent circuit model. This is the model when also dielectric loading is considered. You see that particular portion to the left on the top is corresponding to the dielectric antenna, DRA resonant antenna, DRA loading. And you see, then we can use in this circuit model, we can use the ABCD matrix formulation and compare it to the direct transmission line formulation considering the whole thing by a transmission line model. Here we have to then find out the value of attenuation coefficient, which we obtained after computation through all our earlier results through curve fitting, which we obtained by is given by this formula, and by using them R of course is, as you see, just the raised part of that transmission line structure for corresponding to attenuation plus a part corresponding to skin wave surface resistance rather, which is responsible for current flow within the skin depth. And here, of course, this C is also given by this simple transmission line and Dale like this and circuit analysis. I don't have the time to explain it elaborately. It's already almost 10. And these are the radiation patterns at the different frequencies, both co and cross pole, always having large cross pole discrimination, and more or less always a broadside radiation. That broadside radiation characteristic is being maintained 3.4, 4.2, 5.54, 6.6, all those resonant frequencies. My God, so many, but everywhere you get broadband behavior, broad beam behavior, and broadside radiation. So the resonant frequencies are actually 7 in number, meaning we now have developed this way a heptaband antenna. To the best of my knowledge, this is the first heptaband antenna after our work. Some people also reported multiband antennas like 5 band, 6 band, but first and most probably till date the only heptaband antenna is this one. See the gain value at all the bands, of course usable and good, quite good, quite nice enough. Look at the 10 dB impedance bandwidth also. Well, I'd say the measured value is quite appreciable, quite useful. So what do we have to show you then today? I think one part of our research, application research on DRA, is still not reported by me today. That is reconfigurable DRA. For introducing reconfigurability, I show here a cross slot on a ground plane. Why the cross slot? Because this will eventually feed the Minkowski fractal DRA. Why Minkowski fractal? Already I indicated in order to get wide bandwidth. But why the cross slot? In order to excite two orthogonal modes with equal amplitude and phase quadration. That is to generate circular polarization, CP, which is a requirement in many cases because with circular polarization, your polarization loss is limited to at most 3 dB and no more than that. Below you find the corresponding reference where we have shown all these characteristics, the simulated values, the measured values. You see, again, we have compared between rectangular DRA and fractal DRA. So I find quite interesting results. And another point is also worth noting that the measurement is always giving us better result the than than simulation. So these are the radiation characteristics. And these are the plots for axial ratio, gain and efficiency. See, look at the 3 dB axial ratio spectral wave. There, see axial ratio versus frequency. Of course, it is circularly polarized. We get here clearly the circular polarization bands along with the plots for gain and efficiency. But is that all? We can generate circular polarization. Good. We can generate linear polarization. Good. But how can we generate polarization diversity? That's the point. That we published 2 years back in IET Microwaves Antennas and Propagation. The particular structure is this one. What is the difference of the with the earlier one? Let me see. With the oh, so I think I have to explain. You can see the cross slot over which the DRA would be placed. Now, in this slot, the two arms are really not of equal length. One can be made shorter than the other by switching on a diode. We have direct diode which would, by a virtue of an externally applied bias voltage, which would short that particular arm so that the length of the arm can be changed. And this is the key to introduce polarization reconfigurability. With shorting and thereby reducing the length of one arm a little, we can generate LICP. By applying similar process on the other arm, we can rather generate RHCP. For both the cases, that is LICP and LHCP, you see these are the values of the simulated and measured resonant frequencies as well as impedance bandwidth in both resonant frequencies. In both cases, simulation and measurement are of course quite close to each other, but what interests me more is the impedance bandwidth in order to check its usability. If we take the measured value, which is always, I said, for other cases also, even greater than the simulated value, you see at 2.45 gigahertz, I get 640 megahertz, and at 2.51 gigahertz, I get 775 gigahertz. For LHCP at 2.5 gigahertz, 640 megahertz, and for RHCP at 2.51 gigahertz, 775 megahertz. Definitely an antenna worth considering. Well, what I explained is written here. It's observed that switching the diodes alters the current distribution around the slot, resulting in the two orthogonal nearly equal modes. Nearly equal, of course, because the slot lengths of the arms are equal. This way, the currents are rotating surrounding the slots. See that and see this. It can be observed that switching of the diodes alters the current distribution around the slot, resulting in two orthogonal modes nearly equal in amplitude. So our work is done. We, of course, we fabricated and tested both the modes of operation, AICP and RHCP. Here are the results. So, what do you see? Normal broadband radiation, broadside radiation. Sorry, these are the axial ratio plots, giving you quite some useful axial ratio bandwidth. I mean 3 dB axial ratio bandwidth, not even 4 dB, 3 dB. For LACP, I'm only studying the measured values. The axial ratio bandwidth is 60 megahertz and gain is 3.7 dBi, and RHCP it's 70 megahertz and 3.8 dBi respectively. So now we come to our concluding segment. Today's talk, although you must be extremely tired at the end of the day, but I've tried not to bore you as much as possible without going through lots of mathematics. But I don't know whether tomorrow I think you have to bear with me. You'd be able to, you'd be for the, you'd be forced to follow all those results. I'll try to show you all those theory. I'll try to avoid the detailed mathematics as much as possible still, while showing you the theoretical researches. And as for today, these are our observations and conclusions. I'm reading them out for you. Firstly, gradual rotation of the square DRA tends to excite orthogonal modes which may be tuned appropriately to obtain wideband characteristics. A novel design of wideband antennas have been proposed using fractal geometry. And then fractal DRA designs tend, as we have seen, to shift the frequency upwards as compared to fractal patch antennas, which shift the frequency downwards. Indentation width can be controlled to obtain wideband or multiband behavior. Further, owing to the high Q of slot lines, all frequency bands have narrow bandwidth in the slot load slot fed fractal antenna, except the last band, which has got wide impedance bandwidth owing to the merging of bands due to dielectric loading there, kind of considerable dielectric. And current distribution plots show that increase in fractal iterations not only increase the number of frequency bands, but also results in significant size reduction. Another very, very important point, compactness of the order of 38% compactness was achieved in terms of fundamental frequency. Presence of dielectric loading not only improves the gain of fractal slot antenna, but also provides a wide impedance bandwidth for IEEE 802.11a operation. As I said, this is a band very much amenable to. And a cross-slot aperture coupled fractal DRA is proposed to improve the axial ratio bandwidth of the DRA. It also found the basis to design a polarization reconfigurable DRA. That polarization reconfigurable DRA has also been developed, which is able to switch between LHCP and RHCP just by varying the slot length, employing diodes, switching between two states of the diode, two states, RHCP and LHCP rather, is achieved by using diodes. Pin diodes, these could have been varactors also. We use pin diodes. The antenna radiates with acceptable gain over the entire frequency band. So I've shown you so much of our application oriented work. And these are papers in which they have been reported at different time to time. Published in IJE, in transactions on AP, as well as in IET microwaves antennas propagations. These journals, they are cited quite a number of times. Some good conference papers are also enlisted here in this regard. And not only that, the work resulted in two prizes at conference, one at conference, digital conference Thailand, first prize, and another second prize for MB Chauhan Students Paper Contest, because that was by the student working on that. So, well, today I am not putting up this thank you slide because the simple reason that tomorrow I'll continue. But
Okay.
right now, can we just stop here and go for some questions if you still have energy left for that?
Yes, sir. Thank you very much, Professor Bhaskar sir, for delivering an informative session. There are only two queries on this presentation. First one is, how DR shapes affect polarization of the radiation pattern?
Okay. This question is very simple. We basically work on the rectangular shape by modifying these researches. For the rectangular shape, it's always linearly polarized. Now, we tried to generate a circular polarization by generating two orthogonal linearly polarized the fields, and for that we use these techniques, these maneuverings like rotation, so that the rectangular antenna is converted to a rhombic antenna, and we fed them by using a proper feed line so that the phase difference is 90 degrees between them. But of course, with other shapes which have not been reported today, you can generate other shapes, other polarizations also. But nominally, DRAs are always linearly polarized.
Okay, sir, next query is, would you suggest some professional fabricator for DR antennas? professional fabricator available in India?
Yeah, that's a very good question because we face lots of hardship about that. Of course, we try to fabricate it properly at our lab, but lab and workshop. But you see, of course, there's some discrepancy in between simulation theory and measurement. That's due to a rather inadequacy of that setup. But once I tried that said there's a central government mechanical workshop. Maybe tomorrow I'm just forgetting the name, to the north of Calcutta, and I found that if they can spare the time, they can do very good fabrication. Okay, and you can consult Samir Kolkata also about this matter.
Okay, okay.
But tomorrow, in tomorrow's session, just now I can't remember the name of that central government organization, but they could very nice mechanical work, and they cut these DRA materials with proper dimensions for us. Tomorrow I'll
Okay.
tell you the name.
Thank you, sir. Thank you so much for being too hectic schedule of the whole day, and still you are looking quite energetic and delivering a talk at 9 p.m. and it is like going up to 10 p.m. without not taking much time. I must say final thank you to you as well as to all other participants who are still active in the YouTube channel. Tomorrow we will continue with the second part of this session, and hopefully we will get further knowledge, further information on the second lecture. With this, thank you very much once again. Thank you, Bhaskar Gupta sir, for being with us today, and hope that you will spare time tomorrow also for us as we have already planned.
Thank you, everybody. Good night.
Thank you, sir. Thank you very much. Good night. See you all tomorrow
You
at
are.
7 p.m. Okay, bye.